Now, there is an alternative viewpoint that we discussed in the last class, that if I want to recover Ek, I look upon the moving average model of order 1 as an AR1 for Ek, where Vk is being driven. Remember, this is our original schematic. We assume that the process is actually being driven by Ek. This is the process generating Vk, and we assume that this is being driven by white noise. But now if I have to make a stable forecast from Vk, then I need something, some device which will actually take in Vk and generate this. Okay, do not think that they are in a loop, I am just saying that this is something that I implement in parallel. Okay. And obviously, qualitatively speaking, this has to be in some sense an inverse. Do not think I am taking the physical system and actually tumbling it over or anything like that. It is just a mathematical inverse. Okay. In fact, you can look at this for those of you who work in probably speech processing or a field called source separation, which is a fantastic field in itself in speech processing, in chemometrics and so on, where you are given mixture measurements. And the classic problem, one of the classic problems that is presented in source separation is, there are a few people sitting, like you are all seated here, and I have some 100 microphones recording whatever we are speaking, and we are only given the recordings, and we are supposed to figure out how many people are sitting in the room. Okay. So, that is the problem of source separation. These 100 microphones actually pick up the speech signals coming up from that many speakers in the room, and we assume a certain mixing model, that is the speech signals are actually mixing in a certain manner at the point where the microphone is sensing the audio signal. So, you come up with a mixing model, and you assume a certain mixing model, and you use the mixture recordings readings, and then you figure out what the speech signatures are, how many speakers are there. A simpler problem is I am given how many speakers are there, like M is given for example, and I figure out what the source signatures are. In fact, if you look at the model carefully, the moving average model carefully, it is nothing but a mixing model. So, you are mixing the white noise sources from the past and producing Vk, right. So, it is a mixing model. What you are doing now to recover Ek is demixing. So, you can think of this inversion also as demixing. So, there are so many nice perspectives depending on what you are comfortable with. So, coming back to the point, what is moving average model for Vk is actually an autoregressive model for the recovery of Ek. And we know straight away that any autoregressive model is will produce a stable, in the sense stationary signal, at least for AR1 we know that the C1 has to be less than 1 in magnitude. This is another way of arriving at the same result, very good. Now, there is now this formal setup. Okay. So, we have looked at two different perspectives. Now, we want to extend this idea. Essentially what we are saying is, you will have multiple models when you estimate an MA model, but you will have to pick that one which is so called invertible. Invertible meaning that which generates a stationary Ek, that inverse which actually generates stationary Ek. So, this process is what we have actually denoted by H of Q inverse, and now we are seeking some kind of inverse H tilde for now, call this as H tilde of Q inverse, and this H tilde should be such that when it operates on H, it should yield 1. That means you should exactly recover Ek, right. Just look at this equation here. We have V as He H operating on E, and I assume that Ek is H tilde Vk. So, when H operates on H tilde, I should get this as unity. In fact, it should be the other. So, what I show on the screen is H tilde times H equals 1, but that is also okay, because these operators are actually commutative. That is, Q inverse operating on Q should get me 1, Q operating on Q inverse should get me 1. So, whether you write as H tilde operating on H or H operating on H tilde, it does not matter, they should come out to be 1. You may think, why I have written this way? I could have straight away written this as H inverse. I mean, I could have written H tilde here as H inverse itself. Right? Why have I not written this? Because it is not so straightforward to assume that simply an inverse of H will get me 1. What one needs to do is, you have to actually formally show, that that H tilde is H inverse, and I am just avoiding that proof. The way you show that it is formally H inverse is, you go back to this series that you see in equation 19, which is in, now we have written Ek as an infinite combination of the present and the past signal, but now the coefficients are H tilde. Using this H tilde and using this summation here, and then using the fact that H of Q inverse is described in terms of H, I will have to do some formalization there. I do some multiplication and eventually show that H tilde are indeed the coefficients of the series expansion of H inverse. Right? For example, here when I take an MA1, H of Q inverse is 1 plus C1 Q inverse, and H inverse, that is a series expansion of H inverse, is, as you see on the screen, as you have done also previously in the class, 1 plus C1 Q inverse inverse, and you have 1 minus C1 Q inverse plus C1 square Q inverse square, and so on. One has to actually formally show that your H tilde that you have for Ek is H tilde of 0 is 1, H tilde of 1 is minus C1, H tilde of 2 is C1 square, and so on. But we are avoiding that. You can take it that the H tilde is nothing but H inverse, provided it exists. What we mean by provided it exists is that when I use that H inverse, it should produce a stable Ek. That is what we mean by provided it exists. So, the summary is essentially your H tilde is simply the inverse of H, and assuming that it exists. Okay, so this is how you figure out the inverse of any time series model, and as you can see clearly, even in the inverse the leading coefficient is unity. It has to be, because the leading coefficient in H is unity, alright. And if H is a finite order like your MAM, your H tilde is infinite order, right. Suppose H was autoregressive, what would be the inverse? It will be finite, right, it will be simply 1 plus D1 Q inverse. But if you cast the autoregressive in a moving average form, which we have done before once, you run into an MA infinity process, right. So, when in general this is true, a finite order moving average process manifests itself in the inverse domain as infinite order AR process and vice versa. Okay. But we will talk about that a bit later. Right now, let us talk about inversion. So, the formalization is that the inverse should exist, and if it exists, then we say that the model is stable. Now, before we state the formal result, what we mean by inverse being existing, inverse existing and the invertibility, let us also take some effort in rewriting the prediction equation in a formal manner in terms of the inverse. So, here earlier, if you go back to the previous slide, we wrote this prediction equation specifically for MA1, But now if I am given a general H, how do I write the forecast equation? And the way you do that is using this notion of inverse. So, what you do is you say V hat of k given k minus 1, it does not matter whether you have V at k plus 1 given k or V at V hat, whether you are predicting k given k minus 1 or k plus 1 given k, it does not matter. So, what I have done here in writing the prediction equation for Vk given k minus 1, if you look at equation 22, what I have done is I have thrown away, what have I thrown away? The Ek term, right, because that is unpredictable given any past. What is left with me is the sigma Hn q to the minus n running from 1 to infinity instead of 0 to infinity operating on Ek. But that part is nothing but the H that I have minus 1. Remember that my H is actually in a general, for a linear random process, H of q inverse is 1 plus sigma Hn q to the minus n, where n runs from 1 to infinity. This is my H for a linear random process. So, straight away this identity comes up. So, all I am doing is I am, instead of that summation, I am substituting H of q inverse minus 1, it is just plain algebra, there is nothing magic there. Now, what I do is in place of Ek, so ultimately what do I want? I want a forecasting equation in terms of the model and in terms of the data that I have. This Ek is only an intermediary. So, I have to get rid of that Ek, and Ek is nothing but H inverse V, if it exists, right. So, now I make use of the properties of H and H inverse, and ultimately what is the expression that I get? Sorry, what do I get for V hat of k given k minus 1? Essentially I am asking you to complete that. What do I get? Times something. Generally we look at the width of the parenthesis and say that is how it should be, standard coaching stuff. Sorry? Vk minus H inverse, that is it, on Vk. So, correct. So, how do we write this? 1 minus does it look okay? I know it is Vk, but okay. Okay. So, is that equation okay? I am predicting V at k, and on the right hand side I am saying I need Vk. Something strange, isn't it? Some trap? Somebody needs a phone a friend? Because I can see somebody sending SMSs and finding out what is the answer. Right side one is the? No. Left hand side is a predicted one. Right hand side is your pure available signal.
You could write Vk as q inverse Vk minus.
Vk as?
Q inverse Vk.
Then what happens? Sorry? Yes.
The lead coefficient. The lead coefficient of H inverse is also 1. So the right hand side actually starts on k minus 1 only.
Very good. So this is an independently arrived answer. Yes, very good. Thank you. So that is the main point here. The leading coefficient in H inverse. That is why I emphasized earlier. Just as the leading coefficient in H is unity, the leading coefficient in H inverse is also unity. So, although it appears a bit awkward, the equation looks a bit awkward, it is not. it is just a compact way of writing your forecast expression. If I were to write in an expanded form, then I have to bring in, depending on what H is, H inverse may be finite or infinite, I mean in terms of summation, right. So, instead of breaking my head on that, we should generally we leave it at that. Depending on the scenario, either this 1 minus H inverse would lead to an infinite summation or a finite summation, but regardless Vk does not participate on the right hand side. The first term that participates in the equation is, if at all Vk minus 1, then that should be Vk minus 1. Maybe that is also not there, depends on the model, but that is the first term that you can get at most. So, that is something that you should keep in mind. And I expect you to remember this is like one of the golden equations for forecast. Given a time series model, you should straight away remember this as an expression for one step ahead forecast. When we talk of forecast later on, we will talk of p step ahead forecast and so on. See, sometimes you want to make forecast p steps ahead, like in a game of chess I want to predict the next 3 moves, not just the one move. This is for a one step ahead prediction. Now, given any time series model that is invertible, you can use this expression for calculating your forecast, theoretical forecast, right. I mean, later in practice what you would do is you would replace this H with its estimate and you would replace Vk with its realization. Keep that in mind. So, now we come to the concept of invertibility and formalize it. Any stationary, that is the model for any stationary linear stationary process, is said to be invertible if all the roots of H of Z inverse, and we say at this moment we look at H of Z inverse as a numerator kind of model, but when we move later on we will see when it comes to ARMA models, H of Q inverse can have a numerator and a denominator. In that case we will replace these roots with the zeros. So, the zeros of H of Z inverse should all be outside the unit circle if you are looking at in terms of Z inverse, or inside the unit circle if you are looking at in terms of Z. Normally when we use the word zeros, it is usually calculated in terms of Z, that is a systems theory convention, in which case this condition translates to the root zeros being inside the unit circle. But if you say roots of H of Z inverse, there is a choice that you can make whether you are expressing the roots in terms of Z inverse or Z. If you take for example the book by Shumway and Stauffer, they do not talk of Z inverse or Z, they use this backward operator B. Okay, I find that convention a bit backward. So, I use Q inverse, but whatever, I mean some other textbooks use L for a lag operator. Straight away they specify in terms of the B or the L, which would amount to saying in terms of Z inverse, and therefore the conditions would read that the roots have to be outside the unit circle. This unit circle comes about because the roots can be complex valued, you should understand that. Only when it comes to MA1 model, there is only one 0 and therefore that straight away translates to a restriction on the coefficient. Do not, for heaven's sake, ever assume that invertibility is actually a restriction on the coefficients, it is a restriction on the zeros or the roots which are a function of the coefficients. In other words, do not assume that if I give you an MA2 model, the condition of invertibility is that mod C1 is less than 1 and mod C2 should be less than 1. This is wrong. You have to set up the equation for calculating the zeros and then look at the roots, and if you calculate the roots in terms of Z inverse, those roots should be greater than 1 in magnitude if you are calculating the roots in terms of Z inverse. All right. Now, having said this, there are at least going to be a few students who will make this blunder in the final exam, whichever exam, because you will see a similar condition for stationarity of autoregressive models also. There we look at the denominator of H, but that is for stationarity. Here this is for invertibility. the conditions of invertibility are different from the conditions of stationarity. So, this is a story of invertibility and all the formalization surrounding it, and in that process we have learnt this one step ahead prediction expression. So, to summarize, which means you know that the class is coming to a close, that is your prediction. Okay, let us see if your prediction works out correctly. What are the inputs that you can take? Whatever I have said and the time, there are 2 inputs that you can take to make a prediction. So, to summarize, linear random processes can be expressed as a linear combination of the past, future and present and future shock waves, which are nothing but your white noises. In some schools of thought, it is an IID process, and the descriptions for these linear random processes have very strong similarities with that of the LTI deterministic processes. And when it comes to identifying these models, we are forced to place some restrictions, and one of the restrictions that we placed is H naught should be 1, right, which is not the case in the deterministic world. And the infinite unknown problem is overcome at least in one way by assuming that the impulse response coefficients actually die down after a finite number of lags or whatever, finite number of instants. And that leads us to the moving average models, and the MAM processes are equivalent to FIR models in the deterministic world. In the stochastic world, we figure out if an MAM model is suited by looking at the ACF, which also tells us what is a good guess for M in practice. And among the other fact is that when we sit down to fit an MAM model to a given process or a series, we usually generally will run into multiple models, and we pick the one that is invertible. So, when you use commands like ARIMA in R, which estimate the moving average models for you, there is this code within that routine which picks the invertible part and returns to you. Okay, it does not put that burden on the user, it straight away gives you an invertible